Okay, so now I want to say a few things about explosions, and I need you to look at the two videos that I've put in my list here. Um, and here, let's go to those two videos. So I'd like you to stop my video now, watch those two, and then come back to it. So now, all right. So this is the first of the two videos. So now you've seen the two videos, and you know that there's a small explosion that causes these two cans to blow apart. It doesn't shred the cans or anything, but they get moving pretty fast. And this one here goes to the left, and this one here goes to the right. Okay, now let's think of this as a conservation of momentum problem. Before the explosion, the total momentum, P total, is equal to 0. After the explosion, the total momentum is also going, so this is initially, right? And then final. Yeah, well, it's the same thing, right? P total is equal to 0. Okay, so so now what can we say about the motion of these two things, right? So let's write down that the total momentum, call this can here mass 1, call this one here mass 2. So what we're going to have is mass 1, velocity 1, plus mass 2, velocity 2, is going to add up to 0, right? This is true before, obviously, because velocity 1 and velocity 2 are 0, but it's also going to be true afterwards because that's the law. So let's see what the law can tell us. Let's say that we measured that this thing went off at, I don't know, maybe 100 meters per second. And let's say that this one, I don't know if we're going to need it, but let's just give it a mass. Let's say they both have a mass m1 equals m2, and let's just say it's 0.2 kilograms, let's just say. All right, so we're going to be able to predict what velocity 2 is going to be by doing this. We're going to say, all right, m2 v2 will equal, I'm going to subtract m1 v1 from both sides, so minus m1 v1. Then I'm going to divide both sides by m2. We're going to get v2 is equal to negative m1 v1 over m2. Okay. Now, I didn't think we would need the masses because we did say that mass 1 equals mass 2. So if they're equal to each other, they cancel. And so we get that V2 is equal to the negative of velocity 1. So if this one went to the left at 100 meters per second, then the other one is going to go to the right at 100 meters per second. Yeah. Okay. Now, I want to go back to some notes way back. This is notes for chapter 5. And do you remember this? We're talking about recoil and how if you have a bullet coming out of a gun, then the bullet's going to come out faster and the gun's going to move, and we call that recoil. Now we can understand this in terms of conservation of momentum. You see, before the gun fired, the total momentum was 0. After the gun fires, the total momentum is also 0. But the thing is that the cannonball has some momentum, P ball, going to the right, And so consequently, to add up to 0, right, the cannon's momentum, P of the cannon, has to be the negative of P ball. So that means the cannon has to move to the left. Okay, so let's look at this in a little bit more detail. So I'm going to write down the momentum of the cannonball. So we've got the momentum of the cannonball, P ball, is equal to the mass of the ball times the velocity of the ball once it's come out. And we know that we know that the momentum of the ball to the right plus the momentum of the cannon to the left, they've got to add up to 0. So that means that the cannon's momentum is the negative of the cannonball's momentum. So I'm going to write down P of the cannon, P sub C for cannon, let's say, is equal to minus the mass of the ball times the velocity of the ball. All right. Now, the velocity of the cannon, the recoil velocity of the cannon is equal to the momentum of the cannon over the mass of the cannon. But now I can plug in minus mb vb. So I'm going to have minus m of the ball, v of the ball, over the mass of the cannon. So now let's write this a little bit more neatly. I've got Vc, the cannon's velocity, is minus mass of the cannonball over the mass of the cannon times the velocity of the cannonball. So this is pretty good. You see, the velocity of the cannonball was probably pretty high, but this ratio, the mass of the ball to the mass of the cannon, this is really small. So that means that, yes, the cannon will be moving to the left, but it's going to be a small amount of motion because this ratio, mass of the ball to the mass of the cannon, is so small. Okay, so I hope this helps. And okay, yeah, before I stop completely, let's just take a look at this second video, right? In the second video, the can on the left, the Sprite can, is much more massive than the one on the right. The law of conservation of momentum is still going to hold. Which can is going to go slowly? Which can is going to go real fast? Well, I guess you saw the video, so you already know the answer. Okay, so that brings us to the end of these notes. Before I go, I really want to make sure that you know that our book talks about all of this stuff, all right? So you're going to be looking at section 9-4, conservation of linear momentum. Look at the canoe example. The canoe example is a kind of quote-unquote explosion. And work through the examples. Take a look at the ballistic pendulum problem. This is a classic inelastic collision. By classic, that means very likely to be on an exam type of question. Take a look at the colliding cars, another classic problem. And yeah, all right. So thank you for watching. See you later. Bye-bye.